microgrid. Now, when you talk about inverters, why we are focusing on parallel inverter operation in AC microgrid? What is the reason? Why?
Current rating.
No, first of all, in a microgrid, how do you see the role of inverters?
Solar PV is there. Then.
Very good. All right. So you need inverter. How many inverters?
Depends upon the.
We see multiple inverters are being used in microgrid. Okay, it is not about a single inverter, but we see multiple inverters when you wish to evacuate huge amount of load through a high load current. So instead of one inverter, we keep n number of inverters in parallel to evacuate your renewable energy to the main grid. Okay, and what are the challenges when I keep parallel inverters? So if I keep inverter 1 and inverter 2, and they are both catering to a load, then current I1 and current I2 will add it up I1 plus I2 and go to the load, fine. But it may so happen that there could be a circulating current between parallel inverters also. And hence, analysis, study of parallel inverters in any microgrid will be of serious concern today. Okay, so this is a very, very important concept, and for some extent, it is a a serious concern. How do we handle a microgrid's inverter operation? We do many analysis, but there will be something else happening in the microgrid that we are not aware. So this is one of the deeper understanding of inverters parallel operation. Now, yeah. So when you talk about in renewable energy application, you can just swap into the basement, the right side one. It cut the contents, yeah. Yeah. So in renewable energy applications, inverters are connected in parallel mainly to increase the generation capacity. Most of the PV and wind plants consist of parallel operated identical inverters. Normally what we do, if I have to make something like 50 kilowatt, I will have 10 kilowatt capacity and put them in parallel and get it connected. So they're of the same variety most of the time. So in grid connected mode, all the inverters act as parallel connected current sources. Here our focus is on the parallel operation of inverters in grid connected mode. So here our focus is on the parallel operation of inverters in grid connected mode. So left hand side shows that multi-parallel inverter system connected to a grid. So you could see there is a first inverter, then you have a second inverter, then you have a third inverter. All are connected to PCC and hence connected to a grid. Now to understand more in detail, I think we will try to have a very simplified direct diagram actually for better understanding. So what are the challenges we see? Now there are two different type of actually currents. One is interactive current that is happening or coming from the actual inverter side, and there is a common current after the addition which is flowing through the LG is known as my actually common current. So inverter 1 is releasing current I1, inverter 2 is I2, I1 plus I2 is going to the grid, but I1 and I2 are responsible for certain challenges, so-called interactive currents of inverters coming out of parallel circuits. So both the inverters have identical parameters like L and C. The interactive current which are equal in magnitude and out of phase with each other will flow between the inverters. Magnitude is fine, but if they're out of phase, then they will oscillate between inverter 1 and 2. So the common currents are the ones that actually flow into the grid. So some portion will spoil, and the rest will actually go out of it. So there is a loss of power evacuation due to parallel operations. All right. Normally, we don't experience all these things. We connect it and find we are happy whatever energy is available to me. Instead of 10, if it is coming 9, okay, good. Probably there must be something else. 9 में काम चला देते हैं, है कि नहीं? But actually, there are some internal issues. If you go deeper and deeper, you will understand more. So and the cheaper inverters actually don't have those kind of mechanism to avoid such kind of challenges. They accept it. Single inverter along with their control system. So this is one of the very single inverter system. As you could see, there is a PCC, and then you have LG, and then BG, and 1121 and C11 belongs to the system side, and then you have a reference. I reference, which is, and then I21 is the current being refer or compared, and then finally the current, the error, current control plus active damping is given an input to VO1. So the single inverter circuit, when we see along with the control mechanism, so the figure above represent a single inverter along with its control system. The left hand half is the control mechanism, and right hand side the representation. The grid side current I21 is controlled. Okay, the I21 is controlled because it can be controlled. I can control how much actually power I like to evacuate. Okay. In order to damp the LCL filter resonance, active damping is used in control. The closed loop transfer function between the output current IT1 and the reference IREF is given as I21 equal to G times IREF. Okay, so there is a strong relationship between the output current and the control, and G is more or less called actually closed loop gain. But now we'll expand this to a two parallel inverter mechanism. So this is the interesting business starts here. So if I have two parallel, as you have seen, so there are two current, I21 and I22. They are actually merged to PCC and going to the grid. And both of them actually have a control mechanism. I21 and I22 are being controlled and compared. So what I'll have, instead of a single current, I do have two currents. One is I21 and I22, which is equal to G11, G12, G21, G22, the four different gains of the matrix multiplied by VO1 and VO2, okay, voltages. So now this is for two parallel inverters. Now let's say I do have N parallel inverters. I may be having N parallel inverters. So what will happen? I'll have Nth equation, N cross 1, N by 1, and N cross 1 matrix for the whole system, because it's not limited to 2. It could be 100, it could be 500 parallel microinverters sometimes, okay? So G11, G12, G21, G22 are the elements of the transfer matrix which can be calculated using superposition theorem. So what we do now, we get into the superposition theorem. So we have broken the original network, two parallel inverter into two networks. Okay, so what we have done, superposition, what we do, what superposition theorem says, determine the response. So the superposition theorem says determine the response across an element or a load, making one source present and the rest of the source are replaced by their internal impedances. Okay, so now here we actually two voltage sources. So if you see the first one, we have actually determined the response I grid, making the second voltage source replaced by internal resistance or impedance means short circuited. So we have short circuited VO2. In the second case, actually we have short circuited VO1. Okay. So now what is happening? So the first one I will solve, the second one I will solve and find out what is my, and I can have n number of actually superposition additions. For identical inverters, I think L11, L12, L21, L22 and C11, C12, they are all equal. Considering the effect of one pole voltage at a time, we can split the above circuit into two equivalent circuits. Upon solving these two circuits, the elements of the transfer matrix can be obtained. Is it okay? And then you can solve this both the circuits, and then you can calculate your all the elements of the G matrix. So indirectly, if you see the interactive and common circuit derivation, where I21, I22 equal to G11, G12, G21, G22, VO1, VO2, and where the value of G11 is given by certain equation, G12 is given by another equation, where Gp is popularly known as plant transfer function without grid impedance LG. Gc is the plant transfer function which has LG, and N is the number of inverters connected in parallel, where Gp and Gc, all the variables, omega R, omega R1, everything has been calculated. So for detailed understanding, you can refer to a classical textbook on inverter parallel operation, but this gives the philosophy that for two parallel, actually, this kind of equations you can generate. Now, interactive current can be expressed as a closed loop transfer function where I can say I int, which is equal to 1 upon n GPD upon 1 plus GPD multiplied by IREF1 minus IREF2. And the common current can be calculated as 1 upon n GCD plus 1 GCD IREF1 plus IREF2. So indirectly what we are saying, the interactive current and the common current can be calculated of a parallel inverter mechanism. There could be n number of inverter. You have derived the equation now using nth superposition theorem. So D is the transfer function from error signal to inverter output voltage VO1 for inverter 1, and the same holds good for inverter 2. Hence, D is identical for both the inverters in this case. I think this work we have already published actually in one of the conferences in 2022. Narendra Babu happened to be my scholar, and myself, we both actually tried, just initial day of work actually. So how do we overcome the interactive current? Means we want that interactive current to be nullified, am I right? We do not want anything to happen. Especially the oscillating or circulating current to be nullified. Whatever the current comes actually must go to the common flow actually. For both the currents to be stable without oscillation, the characteristic equations 1 plus GPD and 1 plus GCD should not have poles in the right half of the S-plane. Now, inference for an inverter with the LCL filter to be stable, it is required to ensure interactive and common current stability. The behavior of these currents might be different when inverters with different ratings and dissimilar filters parameters are present. The problem of interactive and common resonance does not occur in L filter inverters due to their first order nature. So this is what the philosophy is all about. Now we'll move to the energy management in a microgrid. This is basically a kind of an introduction. We have already understood what is DC microgrid in the past, but today what we will be interested to focus, that you may be having a peak scenario in the system, because now last class, we have connected the microgrid into a distribution system where the voltage of the distribution system need to be recovered when there is a fault. Am I right? So what we are doing, we are talking about applications of microgrid in a system when they are integrated to a system. Similarly, today's study also focuses on if the system is experiencing a peak challenge, or it could be off peak, or it could be in islanded operation, depending upon the battery's capacity, whether it is fully charged or half charged. Am I right? How you are going to operate, how the microgrid will be operated to see to that the peak of the system is being managed or controlled. So whenever the system is peak, what it expects? The system expects actually the microgrid to help. Okay? Not to draw any energy from the grid. And if possible, give some energy back from your system. That is what the expectations of a microgrid. Similarly, if the grid is having excess energy, so that means the grid is in trouble. All of you please remember, when the grid has either maximum or minimum, both are trouble. It is not a good idea that it has enough power. It cannot balance it out. So when there is excess power available, then microgrids are so generosity to charge the batteries if they are available. But that's the only thing available with microgrid. Oh, kya kar sakta bichara? He has nothing. Excluding there is a battery. If it is not fulfilled, please give some power to charge it. But it should give the control command to start charging. Otherwise, that fellow will sit idle. So if it is charged up to 70%, and you are saying, I will not operate my battery beyond 70% because of the life cycle, but you can go up to 80, let's say, so that 10% margin of the battery can be utilized when the grid is suffering actually. The mother is suffering, the kid will at least help them, okay? So this is what the innovation work actually we're talking about. So this work related to IEEE transition on smart grid in 2017 by Sanjeev Panal and myself. It's a very, very interesting work. 17 means almost 8, 10 years back work, okay? And that time, cracking a smart grid was really challenge, but somehow they appreciated this thought process. And this is an extension of the Nand Kishore Kinekar's IEEE transition power system on DSM using microgrid. But that was a software simulation, and this is a exactly. I think Manmohan is correct. So these two are actually IEEE transition power system and smart grid. They are actually one is hardware, one is software studies. So present impacts of conventional generation stress the carbon-free generation around the globe. Renewable generation is at the top interest of the country due to increase in per capita energy consumption and deficiency of fossil fuel. So as I told you, because it's not about deficiency, we do not want to get into, any more thermal power plants. In the quality of thermal power plant operation, coals required, they are actually not of good quality. There are too much of ash contents in Indian coals. So we normally import from Australia as on today. So, but above and all, we decided not to go for any more thermal power plants. So I think they are ruled out actually. So we have to get into renewable and the energy requirement by all of us. I discussed in the initial my initial talk. I told you, am I right? We are all yes. I told you that actually we are so ambitious to use more energy, and hence the demand has to increase. There is no other way. And to achieve that energy, we need to have renewable. Is the only way to survive. Okay. So many times we believe that actually we are moving into green energy, but the fact is not that. We need badly some energy, and the quickest way of having energy is renewable. Okay. So evolution of semiconductor technology, increased utilization of electronics in many fields, such as automotive, power control, etc. So DC grids are researched again due to simple control, efficient and direct supply to loads compared to counterpart available. So DC grids become a popular thing today. You see, when you're talking about a charging station, when you talk about a renewable integrated charging station, when you talk about actually green hydrogen production mechanism, when you talk about a data center, when you talk about actually a computing facility with 2,000 computers in a single roof, all such buildings are actually now moving towards DC systems. If you see your Apple building, Google building, then all top companies holding more than 2,000, 5,000, 10,000 employees with too much of energy. So slowly people are thinking that can we not operate with a DC grid if possible? Am I right? So instead of avoiding complication, in one go actually you can sort many things. So you can have cycles operating within that. You see, the campuses are like a stadium. It's not a building, it's more than a stadium. The offices, so big. And let's say there are 1,000 cycles. Those cycles can be of battery. There could be some four-wheelers. They could be of batteries. There'll be golf courses. Those vehicles could be battery. Then you have all the PCs. They could be batteries. The lightning is certainly of batteries. We have enough rooftop PVs. Am I right? So you can really plan for a wonderful DC grid to operate most of the modern systems. But the only hiccup in the sense challenge today, the protection and the many MCB protection mechanism for DC, they have not completely matured because the demand is not significant because it's a business model. Okay, you make a product which is being used only by 10 people out of million, so which is not going to work. Am I right? So until unless that is being evolved, probably will not be successful. Now, this is the system architecture I have already given to you in the past in IEEE transaction on industrial informatics, the previous case, or a general meeting paper, if I'm correct. So DC microgrid structure, where we consider there is a PV panel, there is a battery, there is a super ultra capacitor, and you have a grid and three different type of loads. Why three different type of loads? Because one is, some of them are critical and some of them are non-critical loads. So grid interactive DC microgrid system comprises of PV connected to DC microgrid through unidirectional boost converters. Grid side converter like GSC is connected between the utility and the DC microgrid through a transformer or transforming the power from the conventional grid and vice versa. Now, lead acid battery and ultra capacitor are considered as storage systems. Loads are categorized into two types. One is essential load and the other is non-essential load. Now we have the control scheme with us. Let us not spend a lot of time here. For every device, actually, you can have a control scheme, as we discussed earlier, for your battery, for your ultra capacitor, for PV, and yes. Now, when you talk about power flow control strategies, what we are doing, what kind of strategy we are, putting into a controller. All right. So let's say you have a battery. So you have to design actually battery control strategy, By measuring the SOC, you will decide whether it has to be charged, it has to be discharged, considering the other outer conditions. Am I right? So you will measure whether the load is actually more than generation or less than generation within the microgrid, and see the system at which you have been connected is suffering at peak or off peak or islanded. And then you give instruction to your battery what to do. That is what the control strategy all mean about it. So first of all, by doing so, you can reduce the peak demand. By doing so, you can reduce the peak demand using a microgrid. Manmohan, is it correct? You can reduce the peak demand? Yes. So smooth transition between different modes. Okay, effective control and management is possible. Reduces stress on battery, reduces extreme stress on battery, increase life of the storage system, because you basically not forcing the battery to oscillate as and when required in its own way. No. Otherwise, what will happen? Every time it will fluctuate. No. The load is keep on varying. So to give some strict commands, only at the boundary. If it is below 70, you do it, otherwise don't do it. That means you are restricting the charging discharge cycle by 10 to 1 or 2. So the charging discharging cycle become reduced or very, very less compared to a regular cycle if you do not have a control mechanism in place. Covering grid connected and islanded modes, unity power factor feeding to the drawing from conventional grid. So what is the advantage of unity power factor feeding? To and drawing from conventional grid. So whenever you take power from the grid, you take it at unity power factor. Even when you give it at unity power factor. You all must be aware that once upon a time that the Germany grid completely collapsed because of huge amount of PV integration. What has happened actually, because if the system is having maximum percentage related to renewable, and if they are not operating with close to unity power factor, then how do you get that reactive power requirement? So whenever there is a microgrid, if the microgrid actually start drawing, let's say, less than unity power factor or giving the energy with less than unity power factor, and all the microgrid do the same thing, so then how the system will maintain unity power factor? Isn't it? First of all, you made 70% PV and all 70% are not cooperating. So you have to have a huge amount of reactive power. How do you get that? You don't have synchronous machines in place. Thermal power plants are not there. Nuclear power plants are not there. So it is very important to have a broader condition. I think in India, even today, I'm not very sure, is there any restriction? I think we are slightly flexible, but there must be a restriction if you are putting a PV plant privately, then you must provide, today I think we have 0.95 and above, but it should be made unity power factor injection and withdrawal. Now, this is where actually I need your attention, very serious attention basically. Symbols in EMS elaborated as G is grid actually, okay, conventional grid. B means battery, because these are all important when you get into the algorithm. UC represents ultra capacitor, L represents load, FL represents full load, EL is essential load, NEL is non-essential load, NL is no load, I is ideal, disk is disconnected, ABS is observing, SUP is supplying, and BR is the DC bus regulation. So here I think I'll give you one case study. There are, at least 10, 15 strategies, but we'll discuss one study and then you'll be able to appreciate what is happening. So first of all, you come from the start point, okay, and come down, okay. It is grid availability. Grid availability means, if it is yes, what does it mean? That means it's a grid connected microgrid. Am I right? So it says the grid is there. But we do not know whether it is peak or off peak. Once the grid is connected, very good, grid is there, microgrid is operating. Then you check whether it is a peak hour or not. Now, peak hour means if it is yes. If it is no, then it's a different strategy. If it is yes. So what we understand, that means the system is experiencing peak hours and the microgrid control mechanism has to initiate its action. Okay. The moment you say it is, you want me to zoom a little bit? Yeah. Yeah. Is it okay? Now it is clear? The red portion. Perfect. So it is peak hour. And then in the peak hour, if it is yes, what we are expected to do, I think we will avoid not to draw maximum power from the grid and we will try to discharge the battery as maximum as possible. Theoretically, I'm not very sure. Let us get into this and understand. As a layman, actually, that is what my feeling is all about. This is what I will do whenever the grid is troubled, I will not draw any energy from it. Then we are talking about, what about PV? Now, PV is greater than PL or not? Now, the PV, if it is greater than PL, assume that you have excess power. Okay. So, fine, the PV is more than PL. But in the meantime, what do I do with that excess PV? It is not good that PV is more than PL means I'm in trouble now. So I have to make sure that the battery must be in a position to charge it. Okay. So then I get into a position where I check the battery SOC, which is going to be 70%, means already fully charged or not. Now, if I say it is fully charged, it is already, the SOC is more than 70%. I'm going towards right. If it is yes, I'm moving towards a journey which is tougher and tougher. So I say the battery is already charged. So what has happened? The system is peak and the excess PV energy available and the battery is fully charged.
Extra power from both sides.
Let's see what we do. I think grid will start observing. Am I right? This excess energy will go to grid. Okay. And what is B? What is B means what? I told you battery. I means ideal, don't do anything. Or this means discontinue. And what about PV? PV what will do?
Operator temperature.
Node, that is full load. Load will be full load, PV will be MPP, battery will be disconnected, and grid will start actually observing. So this is what one simple logic. Imagine now it looks so beautiful. How many nights actually we might have discussed during 2013-14. Published is 70, too long after 3 revisions, 2.5 years. Got it? I think once you have control on this, I think we can do miracles, because what we are thinking today, probably there are many other operations which we have not realized. You people can realize. Create a situation which is not part of this. And then you move to the next step. Isn't it, Manu? I think wonderful way. So, and these are, you see, they are all kind of strategies. You can bring an additional device to this system. Okay, let's say I will tell you a theoretical thing. Let's say I have a green hydrogen. Am I right? What time I should charge my, operate my green hydrogen production? Now let's say here, I will tell you a very interesting thing here. Now the PV, if it is access to PL, and let's say I do not have a battery. I do not have a battery. What will happen? And the grid is also not there. Then?
Either off MPPT. Either off MPPT.
Not off. You have to derate.
D-rate.
You have to derate the PV. Okay, to its maximum, which is crime, no? Energy crime. So we are not supposed to do it. See, you've invested, everything is okay. God is giving you sunshine day and you are not producing electricity, which is a crime, no? So I can bring a, let's say, green hydrogen electrolyte mechanism where I can say, produce green hydrogen whenever there is excess. And green hydrogen production is not necessary to be a very kind of semiconductor device production where everything has to be continuous or something, you know. You can do whenever energy is there, you produce it. Another IEEE smart grid, right? You need a kind of a situation where you can command and use microgrid for this. And today, all the green hydrogen production units are within a microgrid only, though they are expected to be. Otherwise, what is green? What is green hydrogen? Green hydrogen are those which plant manufacture hydrogen actually based on renewable energy. So green hydrogen plants are connected to renewable plants. And this logic nobody has applied. You apply today, tomorrow you'll have a transaction. Is it okay? Done. I mean, this is what actually, so I mean, dear friends, it's a very interesting philosophy. Now, if you want me to go a little bit more detail for your better understanding, now instead of PV is greater than PL, now let's say PV is not greater than PL, the left side. Move to left side, the red border. Now, if the PV is not greater than PL, so that means I have less PV with me. So first of all, you have to check the state of battery. Now, if it is less than 30, isn't it? Battery cannot discharge. But if it is no, that means battery has some. So battery can start supplying. Battery can start supplying, and the grid is, what is G? Grid. What is I? You are not doing anything because you are managing your own family now. Forget about helping others. And then B is basically, what is B? Battery, start actually supplying. What is PV? Will do it maximum because it is not enough. And the L will be load, will be operating with full load. So what will happen? So whenever the grid is at peak, not able to provide any energy to the microgrid, and you are also not able to meet your own load, then you start discharging your own batteries. Very, very interesting logic, fantastic. And this 30, 70, what we have taken 90 and etc. Somewhere if you see, we have even taken 90. So these are all creative thoughts. So very emergent, you know. And you could see, now let us move to another point.
Liquid supply,
Which one?
And external.
SOC less than 30, no. It is N, no. N means it has enough energy with the battery.
Okay.
It is not less than 30. Okay. So similarly, I request all of you, we have given different strategy for batteries. one category which is 30 to 70, another category which is 90, another category which is 20 to 10 also. So depending upon the smartness, you can keep the boundary. If the situation is too demanding, there is nothing wrong to charge up to 90 and to discharge up to 10. But if the situation is very happy moment, then you can manage between 30 to 70 itself. All right. So I hope you all have you understood the logic of operation of microgrid connected to a main system? Any one of you must say yes. Message, just message, don't talk. Just have you understood the logic that I have explained? The status, the state of microgrid component. Yes, very good, Chandrasekhar. Thank you. So the state of microgrid components depending. So first of all, you check the grid position, whether it is peak or off peak or islanded. And depending upon these three, you check whether your PV is more than load or less than load. And then based on the battery conditions, 30 to 70, 10 to 40, 20 to 90, whatever the conditions, you take an action. And this is known as energy management. What you are doing? Basically, you are managing the energy requirement of the whole system. So now let us understand what are the modes of operation. The first one is going to be peak hour mode. In this mode, the priority is either to supply grid or draw minimum power required for essential loads in grid interactive DC microgrid by ensuring DC bus voltage is within limits. Now, off-peak hour mode, conventional grid, that is CG, is now able to deliver enough power at low cost. Charging of batteries is preferred along with full load supply from grid so that stored power can be utilized locally when peak demand occurs on conventional grid. However, the conventional grid should not be driven into peak demand, which increases stress as well as carbon footprint due to charging of more batteries to full SOC. Now, in case of a islanded or isolated mode, this mode comes into picture when conventional grid encounters failure or outage. In this mode, the DC microgrid operated under all worst scenarios, like generation become lesser than load demand with SOCs, is at critically low and excess generation with battery at high SOCs. Now, load setting is done in the first scenario, and PV converter will be operated at off MPP in second scenario. All right. So there are now I will be talking about many simulation results. So these are the PV models. We have taken maximum power, which is 1000 watt, 250 watt battery will be of 20 ampere hour, very small one, and nominal voltage is 12 volt. It is a simple car battery actually. All right. And then ultra capacitor of 16 volt and 58 farad, 170 ampere. DC link voltage 48. DC load we have taken actually 23 ohm and 46 ohm. Utility phase actually 230 volt, RMS 50 hertz, Indian grid only. And then controllers, we had battery parameters, ultra capacitor parameters, PV parameters, and outer voltage loop. All the parameters to start the first foundation test bed for your DC microgrid. I think you cannot get any material more than that. You just do it, it will work. All right. Now, this is the peak hour mode. Again, this is the outcome of a IEEE transaction on smart grid in 2017, where you could see that different. I'm just zooming it for your slight benefit. Sorry. No. Yes. No. Okay. Yeah. Yes. Okay, the other slide is, now it's I've slightly zoomed. Yes, now it is okay. All of you please have a focus. Okay, so this is your case 1, case 2, case 3, load shedding, and case 4. So we are talking about actually different cases for our understanding. Okay, I'll explain you actually what are the cases and the SOCs of the battery. You could see how it is varying. The voltages, you can see it is 48 volt, but it is fluctuating in between because of the transit periods. Currents you could see. Okay. Now let us try to understand slowly about the cases, and then things will be more clearer actually. Yeah. Okay. So what we're doing here is that, the figures, we have many A, B, C, D, E, F, G, H, I. So waveform under the peak hour mode, A, irradiance, state of charge of the battery, DC bus voltage, PV input current, battery input current, ultracapacitor input current, load current, grid voltage, grid current, zoomed view of few figures, that is C to I, except G at time T1, superimposed waveform of H, that is given actually H and I, and then zoomed view of actually figure C, that is 1, I actually except G at time Ts, and M superimposed waveforms of H and I at instant T5. So the philosophy basically, you focus on two important things here. First of all, you have to look into the grid side. Okay, you have to focus on actually PV output, and you have to look into the battery output. So that it will clearly, the theory that you discuss in the control strategy, you can experience from the hardware during peak hour mode whether it is actually working as per your desired or not. All right. So now, when we talk about case 1, case 2, case 3, case 4, if I go here, could you see the top? You have a case 2, case 1, case 3, case 4. All right. So let us understand what is case 1. Case 1 condition where the PV is more than PL and SOC is greater than or equal to 70. So you have to go to the control logic and see when PV is more than PL and if SOC is more than 70%. Okay, what are the things expected and whether your battery and PV and the grid behaves accordingly or not, you can check from the characteristics. And case 2 where PV is greater than PL, but the SOC is less than 70. Case 3, PV is less than PL and SOC is greater than 30, and PV is less than PL and SOC is less than 30. So that's what actually we have discussed. You can cross verify whether the hardware result is matching with your philosophy of the control strategy. Now, similarly, we can repeat the same kind of analysis for off-peak hour. Okay, you can get different characteristics. Here again, we have actually case 1, 2, 3, 4, and these are the case 1, 2, 3, 4 in case of off-peak hours. So off-peak hours, we say the PV is greater than PL. Okay, I can slightly zoom it a little bit. Sorry. Is it okay? Yeah. Okay. So this is off-peak hours. Yeah, off-peak hours, where PV is greater than PL and SOC actually greater than 90%. Why? Why we are actually going up to 90% here, previously 70%? Because off-peak. Off-peak means you have enough energy. So you must allow your battery to charge.
Right.
Basic philosophy into mathematics. That's all. So people ask why 90%? I have answer with me. Isn't it? Why 70% you have answer with you? So if your philosophy is clear, your logic is clear, I think implementation will be very, very easy. So similarly, PV is greater than PL, SOC is less than 90, PV is less than PL, SOC is going to be 60. And so indirectly, we are trying to operate between 60 to 90 during off-peak hours. Okay, upper part of the battery actually we are going to operate. Now, similarly, we can move to, yeah, sorry. Yeah. Similarly, we can go to isolated mode of operation. Here also we have case 1, case 2, case 3, case 4, isn't it? And you could see that the battery operation is very interesting when it is isolated because slowly it is getting discharged. So here also we have different modes. And these modes are actually slightly different. Here we are considering isolated mode of operation with 90, 95, and 30 and 30. And these boundaries are not limited. So probably I'm not in favor of going for 95%, which really provides too much unrealistic. So probably this can be brought to 85 to 90, which is practical. Yeah. Good. I think this is what we have done in case of energy management study. So a simplified power flow control strategy is proposed for minimizing the peak demand as well as ensuring optimal utilization of renewable energy and storage. A low voltage DC microgrid was modeled by enclosing a PV source, hybrid storage system, and loads to validate PFCS. The performance of the developed strategy is explored under various practical conditions to ensure reliable and efficient operations. The simulation results were satisfactory and the grid remained stable even in case of extreme conditions. Peak demand minimization, uh, diminishing of stress on conventional grid network, uh, pervasive control analysis, fast regulating of bus voltage, flawless transfer between modes, unity factors applying and observing by the conventional grid are observed as main feature of the proposed scheme. Okay, it may looks very, very simple. We all enjoyed them, right? Yeah, but it is 3 to 4 years of hard work. What you learn in last, probably if I mix both the lectures, it is more than 8 years of hard work. Narendra Babu 4 years and Sanjeev Fanala 4 years. So, dear friends, they're all today available to you ready-made because of transaction papers, but it took long time to achieve this course because everything is now done, so we feel very easy, very comfortable. But it takes time, it's not easy. Cracking IEEE transaction on smart grid takes at least 2.5 to 3 years. All right. For a single student, apparently. And so this is what one of my favorite article, Sanjeev Panala and myself, peak energy management using renewable integrated DC microgrid. If you read Nand Kishore's actually IEEE transition power system in 15 and 17 smart grid paper, you will enjoy actually how the story began from actually 2012 and how it has been realized in 2017. So almost 2012 to 2017, the 5 year span, where not me, but 4 to 5 of us, day and night started thinking about microgrid. So we have not limited to the simple smart grid where the North American peoples were much ahead than us. So we thought actually how to go for a different direction to it actually to capture some dominance of our own. So me being a system engineer and getting into new projects of smart grid, I have best utilized my expertise into smart grid and system integration. Is it okay, Manmohanji? Enjoy it. Thank you very much. Wonderful talking to all of you. And probably, I think we are not, I think we are on time, today's lecture. Today is 16th lecture. I think we are as per the schedule. But tomorrow, I may not be in a position to take my class because I'm traveling. So, Manmohan, please announce it. And we'll have a lecture again day after tomorrow.
Okay, so you can see okay. So, dear participants, thank you very much for attending the lecture. Actually, sir has now urgent meeting, so he has left now. And tomorrow there will be no class as sir is out of station. And day after tomorrow, Wednesday, we will be having class at 5 o'clock. Okay. So thank you very much for the rest of the day and have a nice day. Thank you.